Welcome to Frank Stajano Explains. Today's topic is another exam question walkthrough, since this is exam season and exams are around the corner. This time it's going to be a discrete mathematics exam question, one that was set by one of my predecessors before I took over this part of the course. And so I'm going to show you how I think about solving this type of problem as I go along. And if you enjoy this kind of videos, particularly this one, then be sure to stick a like on it, because this helps the channel very much. As I said other times, if you're going to get any value out of going in depth on these exam questions, you really want to try the exam question yourself before watching the rest of the video. So please stop the video now and see you once you've done the exam question on your own in half an hour maximum with closed books. Stop the video, stop the video. All right, welcome back. Let's have a look at this question. Give a deterministic finite automaton DFA with input alphabet A, accepting the language a to the n for n in U, where U is a set of 1 and 2 union n greater or equal to 3, such that n is congruent to 4 modulo 6 or congruent to 7 modulo 6. So the language is a language made of strings of A's, only A's, of some length, and the lengths that are allowed are given by this U. So U is the set of allowed lengths for my strings of A's. 1 and 2 are allowed lengths, and then there's this other thing, which is all the lengths that are congruent to 4 and 7. All right, so if we ignore this part, I can imagine this second set. If the only allowed lengths were the ones in second set, I can imagine how I would do it by having basically 0, 1, 2, 3, 4, 5, which are the possibilities of things congruent modulo 6, and saying that 4 and 7 is the same as 1, are allowed, the others are not allowed. And so I would come into here from some starting state. Or actually, this would be the starting state. The 0 would be the starting state. And I would say if I get 1a, then I'm in state 1, which should be accepted because it's congruent to 7. And if I get another a, then I get in state 2. And if I get another a, and I don't really need to label these arrows with a's, because the a is the only symbol. So let's assume that any arrow that I draw between a state and another is assumed to be labeled by a. And then this one cycles back here. And I need to make 4 also an accepting state. So that would be great if all I had was this, without having the union of these. Now, if I say, well, 1 must also be accepted and 2 must also be accepted, well, 1 is accepted, that's fine, because it's congruent to 7. But if I were to also put 2 as an accepting state, that would not be good, because it means that 2 plus 6, which makes 8, would also become accepted, whereas it shouldn't be according to these rules. And plus 6 and plus 6 plus 6, all the things congruent to 2 would be accepted, whereas only 2 we want accepted, but not any of the others. So how would I do that? Well, if I had only this, then it's easy, because I would just do an automaton with a state 0, 1, and 2, and I would say, okay, if I got 1, then I accept. If I got 2, then I accept. And then if I got any more than 2, then I go into a reject state, and I don't take anything else. So that would be the automaton I would write if I had to recognize just this. how can I recognize these or these, given that my automaton is deterministic, so I cannot branch out into one or the other from the same initial state? Well, I can say initially I go here, so 1a takes me to this state, 2a's take me to this state, and then the third a that I get might take me in here instead, and then from then on I continue here. So what I do is I let me use another color to show this. Get rid of this, and from this one send me into this. I get rid of this. Of course, you would name this state something else. Let's call them x0, x1, and x2, and I don't know. And these are the ones without the x. And now this is a valid DFA for the whole thing, because this part is catered for by this initial runway, let's say, and then this part is this loop that I get into, and I get into the right sync place so that it's still congruent to the numbers that I had said before, modulo 6. So I think I'm satisfied with this solution here. Now, what does it mean for a language over an alphabet sigma to be regular? That's pure bookwork, so we don't have to waste any time on this. Just look it up. It means it can be recognized by DFA, for example. C, a subset U of the set of natural numbers is called ultimately periodic. I've never heard this before. If there exists numbers big N greater than or equal to 0 and P strictly greater than 0, such that for all small n bigger than or equal to big N, N is in U if and only if N plus P is in U. We have to disentangle this and see what it really means. Can I come up with some examples? Look, if a number is in there, then a number plus p is in there, which means a number plus p plus p plus p. So all the things congruent to this number modulo p should be in there. It kind of suggests that these subsets have to be infinite to be ultimately periodic, because anytime something is in there, then all the things congruent to p have to be in there, of which there's an infinite number. Let's see. Explain why every finite set of numbers is ultimately periodic, according to the above definition, which suggests I was wrong. So every finite set is ultimately periodic. Why would that be? Because we only start from things bigger than big N. So yeah, so I would say if something, if I have a finite set of numbers, there's going to be a maximum to this set, and if I take a big N that is bigger than that maximum, then this condition is going to be vacuously true for anything that is bigger than big N. Then this condition holds, because there's nothing that could ever violate it. There's no numbers there, so that's fine. So I was wrong when I thought that this meant that ultimately periodic subsets had to be infinite. They can be finite. It just means that N exceeds the maximum, and then this rule is never invoked. Okay, 2 marks in the bag. Let L be a regular language over the alphabet A only one symbol. Okay. By considering the shape of paths in the transition graph of any DFA with input alphabet A, or otherwise, that's kind of a strange way to say things. It's like saying, well, do whatever you like. You could do what I suggest, but it's just a hint. Okay. You don't have to consider the shape of paths. It's a helpful thing if you consider the shape of paths. If you want to do some other way, that's also fine. So what should we do? Show that the set of natural numbers such that a to the n strings of a's of length n are in L is an ultimately periodic set of numbers. Let's figure this one out. And it's 8 marks. It's most expensive, the most worthy part of this exam question. So let's pay attention. Let L be a regular language over the alphabet A. This means L is a language made only of strings of A's. Okay. By considering the shape of paths, never mind that. There's a hint. Show that the subset of natural numbers, which is the length of the strings in our language, is an ultimately periodic set of numbers. What would that be? The constraint I have on L is that it's a regular language. So these numbers here are lengths of strings of A's in L, where L is a natural language. And this hint says, by considering the shape of paths in the transition graph of any DFA. Well, the fact it's a DFA means there's a finite set of states. And if any strings at all are accepted in my language, this must be at least an accepting state among this set of states. Because the set of states is finite, if the set L contains infinitely many strings, then at some point some of these strings will be longer than the possible distinct transitions between the states, since there's only a finite number of states. And this means I will hit upon states that I've already visited. So there will have to be some kind of cycle that includes an accepting state if my language accepts an infinite number of strings. So if this is the case, there's a cycle with an accepting state, then clearly if I revisit this cycle, every time I do one pass through the cycle, I have one more string that I accept for whose length is the length of the previous string I accepted plus the length of the cycle. So that is nicely correlated with this p. So if p is the length of my cycle, then if I accept a string, then I will accept a string of length that thing plus p and plus 2p and 3p and however many p's I like. So that's nice. And if my loop has more than one accepting state, then this happens in several other places. In fact, that's the same thing that happened in the thing we produced as our answer for part A. We had a cycle and there were two accepting states. So everything that is p away, p being 6, anything that is 6 away from this one will be accepted. Also anything that is 6 away from this one will be accepted. That's fine. Nothing stops my DFA from having more than one cycle, and in that case the cycles would have different lengths, and if they have different lengths, there would kind of be a different p for every cycle. So I'm not too sure how that would work with the ultimately periodic business over here. So let's have a closer look. By considering the shape of paths in the transition graph of any DFA, that's the hint that's given to us. Show that is an ultimately periodic. So what would be the shape of paths? As we said, we get into this DFA, and if the set of strings accepted by L, if the set of strings in L is infinite, then there must be at least one cycle. Now, could there be more than one cycle? In general, yes. But actually, if I have only one symbol in my alphabet, which means I cannot say for symbol A go this way, for symbol B go this way, for symbol C go that way from the same starting state. If from every state I have only one and only one place I can go to, then there can ultimately be only 0 or 1 cycles in my graph of states. If there's 0 cycles, then the set L is going to be finite. If there is a cycle, then L may include infinite strings, so long as there's one accepting state in L. But there's no way that I could have another cycle, because once I get into a cycle, if from every state I can only go to one more state, there's no way I could branch out into another cycle. I get stuck into that cycle, and that's I cannot go anywhere else. So either I don't go into any cycle, or except for the kind of irrelevant cycle of non-accepting things that I had over here. I mean, since from every state I have to go somewhere, I get stuck in an infinite loop here, but that's not the kind of cycle we're talking about. Anyway, you see what I mean, I hope. So we've established that because the input alphabet only has one symbol, then it is impossible to have more than one cycle. I can have at most one cycle in my DFA state transition diagram. So this means that actually the shape of paths in the transition graph is always going to be essentially the same as this, which I drew before. It's going to be some kind of runway, linear runway, and a cycle at the end. And the cycle could degenerate into just being this type of cycle. So actually I can say that the first thing I drew over here was also an instance of this, with a cycle being this. And in fact, the cycle, I mean, I don't have to be minimal. I could have a cycle. Let me draw another version. I could have a state transition diagram like this with a cycle made of states that are all non-accepting. So let's say that this one accepts this. And this is a language where all I accept is a string of 1A that gets accepted, and then any other string, however long, ends up in here, and it just gets stuck there forever. So this string, this DFA only accepts this string and no other. And if it had this, then it would accept also the string AA and no other. And if I don't have any accepting states in the final loop, then I have a finite set of strings accept. Okay, so great. So I think we are getting to earning our 8 marks. By considering the shape of paths or otherwise, show that the set of lengths of strings in language L is an ultimately periodic set of numbers. Well, it is, because the shape of paths is going to be that which we said, so runway plus loop, or runway. Yes, I'm going to say it's always going to be runway plus loop, with the loop potentially not containing any accepting states, in which case the language is finite. And then what's needed to do a bit more formally is to say, if my DFA state transition diagram has this shape, then the set of lengths is an ultimately periodic set of numbers. And the property for being ultimately periodic is that there exist numbers big N and P such that blah blah. And the number big N is going to be any number bigger than the number of states I have, and the number P is going to be the number of states in the loop that I have, provided that there is at least provided or not provided, because otherwise it's excluded by N, so I don't have to care about that. And P is going to be just the size of my cycle. So with that, having defined the DFA in this way, let's prove that what comes out is ultimately periodic by following the definition here. So is it the case that for all n bigger than n being the number I chose to be bigger than the number of states in the DFA, n is in the set if and only if n plus p is also in the set. So let's first prove that if n is in the set, then n plus p is also in the set. So we first do this direction of the implication. So if n is in the set, it means that a string of A's of length n, if I feed it through my DFA, and we said that n was greater than the number of states, so I'm already in the cycle because I'm repeating something. If this n is in the set, then it means I'm landing on an accepting state. So wherever n ends up, this one, for example, well, then this one is an accepting state. Now, because there is this cycle, if I walk through the cycle one more time, which is n plus p length, n took me there, plus p takes me there again, because it's a cycle of length p, and therefore n plus p is in an accepting state, and therefore is in U, and so I have proved this implication. Great. So now how to prove the implication in this direction. So I have to prove that if n plus p is in U, then n is also in U. Well, that's basically the same with the subtraction. If a string of length n plus p takes me somewhere that's an accepting state, then a string of length n plus p minus p, which means one less go around the cycle, takes me there. So it's easy if I can persuade my adversary that n plus p already include at least one cycle. And it does, because I said that n was going to be greater than big N, and big N was the total number of states. So I am sure that if I do n plus p, once I've done n, I'm already somewhere in the cycle. And so plus p I can only do by going around the cycle again. So it's okay to take it back. And if I take it back, I'm not risking considering whether I have to go back into the runway. So this is fine. And so if I write this out in some kind of legitimate formal way, then I will bag my 8 marks. Great. So what about my final 5 marks over here? Conversely, show that if U, a subset of natural numbers, is ultimately periodic, then this set of strings of A's whose lengths are in U is a regular language. Okay, so this is a set of strings of A's whose lengths are in U, which is ultimately periodic. And I need to prove that it is a regular language. And the way I like to prove that it's a regular language is to build the DFA for it. So if I'm given a U that is ultimately periodic, how can I build the DFA for this language made of strings of A's with the lengths in U? I would say, well, if U is ultimately periodic, then by definition of ultimately periodic, there exist numbers big N and P. So big N and P are going to help me build a DFA of this shape, where P is obviously going to be the length of the cycle, and then N is going to be something such that I don't care about things before I get into the cycle, but once they're bigger than a certain size, then they will have to be stuck in the cycle and keep on repeating and be congruent to P and all that stuff. So this sounds like a good plan, and that's my plan for building the DFA. I have to be slightly more specific about how I do that, and also I have to say where I put the accepting states. Once I have built my DFA, I have shown that the language recognized by the DFA is regular, by the definition of regular. And I think, to be super strict, I should also convince you that the DFA built in the way I suggest recognizes precisely this language. So no string other than those in here are recognized by the DFA, and all strings that are in here are recognized by the DFA. So first let's say exactly how to build this DFA, and then we have to do the 2 directions of this, showing that the DFA matches the set as defined here. So as I said, P is going to be the size of my cycle, which is going to be at the end, and then the runway. How long exactly does the runway have to be, and where are my accepting states going to be? So there is some leeway in the definition of n, it is not the case that the set U is uniquely defined by n and p, because it is uniquely defined by its set of numbers. And these n and p are a high-level description of a property that this set of numbers enjoy, but the same n and p define a property that many possible u's might match. So basically, the big N says, below this amount, don't worry about the repetition to infinity. And after that, then you have to make sure that anything that's in there, then all the things congruent to it, modulo p, are going to be in there, provided they're bigger. But below that, basically anything goes. And so if I say n is 1000, then whatever p is, then all the u's that I can make with anything I like below 1000 are going to be indistinguishable if all I know about u is n and p. So clearly n and p are insufficient. So I have to say, well, give me the set of numbers in u, and let's have a look at all the numbers that are smaller than the n you've given me, because these ones I don't have to bother about repeating them. I just have to pick them one by one. So all of these I'm going to put in the runway. I'm going to make a runway. Make a runway. So things that are strictly less than n are going to be in the runway, and I'm going to make accepting states wherever there are the corresponding numbers in the set U for the things that are smaller than n. Okay, so for example here and here, I don't know, whatever. Then after n, I go into this loop. So the one of length, string of a's of length exactly n is going to be the first state in the loop. So this is going to be a, and this is of length exactly n. And this is going to be the first state that is in my loop. This is just to point at it. It's not to say that it's necessarily accepting. I haven't made a double border here, just made it thick because I was pointing at it. And from then on, there's going to be 0 or more accepting states somewhere in here, and then they repeat with period p. So that's how I build my DFA, given the set of numbers, and also given this n and p by my adversary, let's say. So now I have to prove that this DFA exactly recognizes this language, the set of strings of a's with numbers in U. Well, it becomes almost tautological because by construction it does, because that's how I built it. So all the numbers n, all the numbers small n, which are smaller than the big N, are accepted by my DFA because I built it by sticking accepting states in all the places where I knew that a member of U was there. All the numbers bigger than or equal to big N are on the loop, and so they enjoy the property that if one of them is accepted, so if one of them is in U over here, then it's itself plus p is also in U, because I just go around the loop, which is size p, one more time, and I hit upon the same state, which if it was accepting before, it still is accepting. And then the last thing I have to prove is that no string this DFA accepts no other string than the ones whose lengths are in U. And well, the only accepting things are the ones with accepting states, the ones on the runway that have a one-to-one mapping to the numbers in U that are smaller than the big N. And the ones on the cycle, there's a finite number of them because the cycle is of finite length, namely P. And I can enumerate each of them and say that they match things in my set U. And then for anything else, that's just the repetition given by the congruency modulo P, and there is no other length is accepted by this, because the only accepting states are the ones that we have already identified. And finally, so therefore I have got to the end of my exam question and I can bag my last 5 marks. I hope you enjoyed this, and I hope you do well in your exam coming up soon. Stick a like on the video if you like all this stuff.